presentation today. First of all, I will just introduce, which I think most of us know what is VDTN and what is VNet, so I will just try to make it quick. And then in the coming slides, I will show a few of the routing schemes which are already there in the literature. And before going to that, this is a kind of a survey paper which was originally submitted in this conference. But after showing you some comparative summary of those routing protocols, I also am going to share some of our proposed work in one slide, possibly, which we have submitted to some journal. So it's some of kind of obligation on me not to discuss the whole scheme, but I will just try to explain what we have done. And then in the end, I'm going to come up with some research roadmap, which we guys or the researchers need to have a focus on. So starting with the introduction, long time ago, when even I was not born in 1970, there was packet switching things, and in fact, still in 1980 I was not there, but we got TCP and IP, and then later on we come up with the internet thing, and then there was a lot of research and a lot of development in the internet paradigm, and we can see the straight line going ahead, and still we are focusing nowadays, we are focusing on changing some main architecture of internet as well, for example, ICN and CCN and other infrastructures. But in the meanwhile, after 1990 specifically, we got a research paradigm shift towards wireless networking. And when we talk about wireless, we have a lot of research, but today I'm just going to talk about DTN, which stands for Delay Tolerant Network. Because there are some networks and there are some scenarios where we cannot assume end-to-end connectivity. And when there's a lack of end-to-end connectivity, so it means there will be a delay. So delay tolerant applications are introduced in the market. Before going to DTN, just to overcome what is VNet, we all know it's one of the promising steps, one of the promising technology towards future. And I try to make my presentation a little bit colorful by putting some colorful pictures. But research is never colorful, so bear with me. And we have some characteristics which we should keep in our mind about vehicular ad hoc networks. That is, they have always high mobility, especially on highways, and even we have now good sports cars, so nobody cares about urban areas as well. And we have unpredictable network density. We have delay-bound communication, so here we come for DTN and the delay-tolerant applications. And we do not have end-to-end connectivity and so on. There's a huge list. We all know about it. So I will switch to now. Basically, we have two kind of scenarios in vehicular ad hoc networks. The other one we call it about the dense scenario. Maybe all of us have seen one example in Las Vegas during the past few days. And the other one is kind of a sparse highway situation where we have very less opportunity to connect with vehicles. So keeping these two scenarios, I will move on with the presentation. In order to mitigate or in order to cope with the dynamic topologies, basically VDTNs were introduced, and they are mostly preferable for those applications which are not depending on real-time data. And there are a lot of examples, and of course we need to enable some connectivity in those kind of diverse scenarios, and for that purpose DTN has been emerged into vehicular ad hoc networks. And this new field, whenever we have a new field, it always comes up with some problems. There are always challenges which we are trying to solve. So routing is one of the challenge in that, and back in our laboratory in my university, our main focus is on dealing with routing, so that's how we started our research by investigating some current protocols. So I'm going to summarize a few of them which are selected and presented in this paper as well. The very first is probabilistic bundle routing scheme. And before I start describing this scheme particularly, let us recall that we have RSUs on the roads, roadside units, and we have V2V communication, V2I, and so on. So basically in original, in real time, we cannot say that all RSUs will cover the whole entire segment of road. there is always some gap, which we call uncovered area or some a black hole area where there is no connectivity to the vehicles. So keeping that scenario in mind, this protocol has been designed where they believe, the authors believe that communication is possible by over-relaying data through the vehicles. So in this scenario or for this paper, their application was, or their focus was that we have two RSUs which have some, one has data, for example, source RSU has some data to send to this RSU, which we call destination RSU. So the basic idea is to broadcast the packets or broadcast data to all the vehicles passing by the source RSU, and then those vehicles will take that data, and if some vehicle will come up there over here, and it will just give the data back. But in this scheme, what they try to do, they just try to select only one vehicle. They just try to minimize or control the data replication within the network overall. So in that case, basically, PBSR or probabilistic bundle relaying scheme, it calculates the release probability by utilizing the speed of each vehicle. So the, how can I say, the summarizing point is that every fastest vehicle is selected if any among currently associated vehicles with source RSU. So it means that when the first vehicle will enter into the coverage area of source RSU, it will not directly transmit the data, but it will hold on, and it will wait for another option. And if it gets the better option, it will transmit that, or it will select that vehicle with the fastest speed. Otherwise, when this vehicle will about to leave the coverage area, it will transmit its required data to be sent to the RSU ahead. That is the main theme of this scheme. So, yeah. And then the second, you can say research or second routing protocol which we discussed in the paper, it was published very recently, just like 2 years ago maybe. Yeah. And that was adaptive carry store forward scheme, and it was published in communication, IEEE communication letters. This scheme basically applies the same, just like previously, as I mentioned in here. This scheme also applies or takes the same scenario, but here we're not talking about data to be sent between RSUs. Here we are trying to provide some services to a car which is now in, which has lost the connection with any of the RSU. For example, this is RSU 1, 2, and this is uncovered area. So now this car has no connectivity. So in order to provide some extended connectivity, you can say, this idea has been proposed, where, for example, we have vehicle V0, and it's about to leave, or it is already in the uncovered area. So maybe the other vehicles which were previously here, but currently they are there because of their speeds and moving mechanism. So, sorry, one of these vehicles can be selected as a relay because there is a possibility that one of these vehicles will be in a contact or in an inter-vehicle communication range. So this vehicle can act as a relay to provide some connectivity to this vehicle. So the scheme was basically that, for example, we have RSU1, so it selects the node which provides longer connectivity. Now, the mechanism was defined how to evaluate that which vehicle will be providing a longer connectivity, so it was depending on its speed. But there was one assumption which was very hard, that's why I gave it a different color, which assumes that this scheme assumes that V0 is supposed to restrict its speed in order to get the longer connectivity. So even though while I think writing a manuscript or while performing simulations, it's okay, but in real time, no one would like to compromise on its personal speed on the road. The third scheme which we discussed in this paper was distance-aware routing with copy control. As the name shows itself, that this scheme is basically copying with the data replication problem. And here basically we have some urban scenario where this scheme determines whether or not to transmit data to their neighbors, basically, to their encountering vehicles or their neighbors. But they follow, or their decision depends on two basic principles. The number first is that by using some GPS service, if the location of destination is available, then the things are very simple. We will just select that vehicle which is going to meet my destination very quickly. But if this information is not available, then we have another principle, which means that motion vector of each vehicle will be shared by exchanging beacon messages, which are very common in wave architecture or other service and control channels. We have that experience. But what is motion vector? Motion vector is basically, according to the authors, they define motion vector as a speed and direction of, or the future direction of vehicle. Because when we use GPS, we provide some input to our destination every day or every time. So it can decide our motion vector, that where we are going in the coming or in the coming junction. So that motion vector will be shared with between vehicles. If, for example, if vehicle B has some data to send, and the destination is maybe on that part or some other part, it doesn't know the destination. So it should send, it should not provide, or it should not transmit data to all the vehicles, but it will just select those vehicles which are moving into the different directions from each other. So for example, in case of vehicle A, if its motion vector is, or its the destination is towards the left side, and also motion C, or maybe motion C is, or sorry, vehicle C is going straight, where the vehicle itself is also going. So it will not give the, or it will not give the copies of data to C vehicle, because they are going on the same path. But it will only give data to vehicle A, just to control the copies in the network. The fourth paper, which was provided with the summarized in this paper, was shortly it's called DAWN, which stands for Density Adaptive Routing with Node Awareness. DAWN basically introduced some utility incremental value. It's quite impressive name, but actually it was based on the age of packet when it was initially generated. So it stores that time or that hop count. And basically the very simple mechanism in this routing protocol was that the packets will be given priority on the basis of their age, and age will be calculated from their original time when it was generated. So those messages which are older or which are oldest, they will be only transmitted with every encounter, not all the messages. So that's how it works, and of course this kind of a scheme will come up with some minimized throughput or maximized throughput and minimized overhead, because we are also controlling some copies. So that's how it works. The fifth one, the last of today's presentation, actually there is a sixth one in the paper as well, but this is GOPS, which was published, let's say, a little bit kind of outdated paper. I can say that it's published a bit few years ago, but the reason why we included this paper in, or this routing protocol in our paper, because in our manuscript which is published, we have connected this scheme with the latest one. So this scheme is basically a baseline for the latest scheme, which is called as GeoSpray. I will show you in the coming slide. Basically, GOPS is completely depending on GPS, or geographical location. So mostly we know that navigation systems apply some shortest path algorithm, and usually they also give us with the estimated time arrival when we drive a vehicle, or when we just search in Google as well, so we get the estimated arrival time. So using that concept, in this protocol, they basically are they are mainly depending on the nearest point to destination. So for example, if there are 3 vehicles starting from the same point, and one of them has a packet to destination somewhere here, they already put their information on their personal GPS independently. For example, the red line shows the path of A, and the black line is the path of B, and the green line is the path of C. But destination is somewhere here. So now, if they share the destination information with each other, they can easily figure it out that who will be going to the nearest point of destination. Because going directly towards destination, then the problem is solved. But if not, who is going to the nearest point of destination? So here we can see that this is the nearest point, but here A is going, so A cannot be an option at all. Then we have only two options left, that is B and C. So by this figure or this scenario, we can say that only C is the appropriate carrier for this packet. So C will be selected as a potential forwarder. But remember that this scheme was proposed for single copy. There is no multiple copies, just the message is being forwarded in a single copy manner, that's it. So that's how it worked, and the main contribution of this protocol was to introduce us with the term METD, which is minimum estimated delivery time, or time of delivery. And this was calculated time to the nearest point, and the average speed of current vehicle, and remaining distance between nearest point and final destination. So by applying this formula, we can get the value of this variable, that is METD. So any vehicle with the minimum METD value among neighbors would have been selected as a forwarder. Coming to the comparative summarization of those protocols, this was the protocol I was talking about. I didn't include this in the presentation, but it is basically it depends on GOPS. The basic idea is of GOPS, but in GeoSpray, the only difference is that they are working on multiple copies. And this paper was published in last year, 2014. We have different metrics, or we have different comparative metrics. For example, some of these schemes are depending on infrastructure, which means they must share some information with RSU. And some are depending on location. Actually, most of them are depending on location. And then what were the topology assumptions is summarized in the paper. So if anyone interested, they can read our paper. And also what kind of implementation was there for each paper, it's also given in the table. And what was their main target to achieve? So that wasn't taken. Okay, just if I have time, so I will just
5 minutes.
5 minutes. Oh, I have a lot of time. So this was our proposed scheme, which we actually targeted. If I would like to take you back to this point, because this scheme was recently published, and we targeted some drawbacks of this scheme, and because it assumes that the vehicle should adjust its speed, and all of the decisions are taken at the RSU level in this scheme. So we just shift the idea that a vehicle itself should be capable of taking a decision. And also it should not adjust, or it should not depend on the speed or some of those kind of hard assumptions. So our scheme was, it's a quite complex figure, but anyway, I will just try to explain that. Previously, RSU was selecting just backward relays. But in our scheme, we are also focusing on what will happen when even those backward relays will not be connected to RSU. So where this vehicle will go. So we also expect to have some forward relays as well. I mean forwarder relay selection as well. So there should be some clear mechanism to select those relays, so that this vehicle V0 should be provided with connectivity throughout the way as much as possible. And in our scheme, we are not depending on RSUs. We are just making calculations on our own onboard units and vehicle itself. And we are just exchanging some messages, which is quite normal in Linux. And we are just maintaining a neighbor list. And because of those neighbor lists, we can grab some data and we can process and select backward and forward relay in advance. Actually, this paper is submitted to some journal, and it's kind of under review, and so that's why I didn't include the whole information. So after, basically what was the motivation to write down this paper was to let us think about what is the future of delay tolerant networks in vehicular environment. We should move on with some new ideas. So basically, every routing protocol in Vehicular does not, how can I say, does not assume both environments. Some are specifically for urban and some are specifically for highways. But the missing thing is that most of the time I'm talking about, maybe there are a few words, but very limited. But most of the time, they are specifically for some kind of environment. But what if a vehicle is connected or has been going through the connectivity by having some highway focused protocol, and all of a sudden it enters into the urban area? So how to switch the topology? So that is the main point we should think of while designing some routing protocol for Linux. And also, some important thing is that maybe in future we should have some artificial intelligence equipped vehicles where we should have some routing mechanisms to minimize the trade-off, because always there's a trade-off in delivery ratio or end-to-end delay and overhead. When we go for minimizing the delay, our overhead is increasing. So we should have some mechanism to make it balanced state. And also, when we talk about DTN, so as we know, the basic idea is to manage the buffer in terms of bundle. Bundle protocol is the basic architecture. So still there is a lack of works dealing with buffer management for particularly bundle kind of architecture for Vehicular attack networks. Thank you very much for our session, and these are.
Thank you so much. Do you have any question? No question? Yes, sir. Thank you.
In your work, are you also considering the effect of Wi-Fi network? For example, if cars are exchanging the neighboring list, maybe it will generate the neighboring list in some particular time interval. And if it is our case, maybe there will be many cars, so such exchanging traffic will be the cause of some network congestion like the presence. So maybe I think if you are not currently considering about it, it should be that we consider in the future.
Oh yeah, thank you very much for your comment. But I would just like to give some answer to that, is because we know that in the upper, in the lower layers, or in the upper layers, we have 82.11p, and we have some mechanism to exchange some beacon messages. So it's a very quite normal assumption that the neighbor list can be integrated or compressed in beacon messages. So I think it's quite normal to exchange the neighbor list, and because we have no limitations of battery operated things or something, so we can have a good processor chip to calculate or to solve this problem. But anyway, of course, there will be some network condition, yeah, in terms of urban environment, for sure. Thank you.
Okay. Do you have any question? Any other question? I think that in cabinet scenario, it would be interesting to combine DTN with 3G technology, because sometimes in the sparse scenario, you have never the opportunity to send the data packet, and maybe you have a 3G connection, you can send the data packet to a server, and then from the server you can achieve a ride to many more vehicles in a more extent